The paper mill process involves multiple stages to convert raw materials, primarily wood, into finished paper products. Here's an overview of the key steps. 1. Raw material preparation. Wood sources, for example, logs, wood chips, recycled paper, are collected. Logs are debarked and chipped into small pieces for easier processing. Recycled paper undergoes deyanking and cleaning to remove contaminants. 2. Pulping. The wood chips or recycled fiber are turned into pulp, using two main methods. Mechanical pulping uses grinding and refining to break down wood fibers. Chemical pulping uses chemicals, for example, sulfate or sulfite process, to dissolve lignin, separating cellulose fibers. 3. Pulp cleaning and refining. The pulp is screened to remove large debris. It is refined to improve fiber bonding, which enhances paper strength. 4. Bleaching optional. If white paper is needed, bleaching agents like chlorine dioxide or oxygen are used to remove remaining lignin and whiten the pulp. 5. Paper making process. The pulp is mixed with water and additives, for example, starch, dyes, fillers, to form a slurry. The slurry is sprayed onto a moving wire mesh to form a wet sheet. Water drains through the mesh while fibers begin forming a web. 6. Pressing and drying. The wet sheet passes through rollers to squeeze out more water. It then moves through heated drying cylinders to evaporate moisture. 7. Calendaring and finishing. The dried paper is pressed between smooth rollers calendars to improve texture and thickness. Surface coatings, for example, gloss, matte, may be applied for specific finishes. 8. Reeling and cutting. The finished paper is wound into large rolls. These rolls are cut into smaller sizes depending on the intended use, for example, printing paper, packaging, newspapers. 9. Quality control and packaging. The paper undergoes quality checks for weight, thickness, brightness, and strength. Once approved, it is packaged and shipped to customers. 1. Raw material preparation. The primary raw materials for paper making are wood, recycled paper, and non-wood fibers such as bamboo, straw, or cotton. Wood preparation. Log debarking. Logs are stripped of their bark using mechanical debarking drums or high-pressure water jets. Chipping. The debarked logs are cut into small wood chips, typically 1 to 2 centimeters, to ensure uniform pulping. Chip screening and storage. The chips are screened to remove oversized or undersized pieces before being sent to storage silos. Recycled paper processing. Collection and sorting. Waste paper is collected, sorted by quality, and transported to the mill. Deyanking and cleaning. The paper is shredded, mixed with water, and treated with chemicals to remove ink, adhesives, and contaminants. Pulping. The clean fibers are reprocessed into pulp, similar to virgin wood pulp. 2. Pulping process. Pulping breaks down wood fibers and separates cellulose from lignin, a glue-like substance holding fibers together. There are two main pulping methods. A. Mechanical pulping used for newsprint, magazines, involves grinding wood logs or chips against a rotating stone or disc refiner. Uses little to no chemicals, making it less expensive. Produces high-yield pulp. About 90 to 95% of wood is used, but paper has lower strength and yellows over time. B. Chemical pulping used for high-quality paper. Uses chemicals to dissolve lignin and free the cellulose fibers. Produces stronger and more durable paper with better aging resistance. Common chemical pulping processes. Kraft sulfate process, the most widely used method. Uses sodium hydroxide NaO and sodium sulfide NES to break down lignin. Produces strong, brown pulp. Can be bleached for white paper. Byproducts like tall oil can be recovered and used in other industries. Sulfite process uses sulfur-based chemicals to dissolve lignin, produces weaker, but whiter pulp, less common than the Kraft process due to environmental concerns. 3. Pulp cleaning and refining. After pulping, the raw pulp contains fibers, water, and residual impurities that need to be removed. Screening. Large particles like knots and dirt are filtered out. Washing. Water is used to remove residual chemicals and lignin. Refining. Beating. The fibers are beaten to improve bonding strength and paper quality. Bleaching. For white paper production. If white or bright paper is needed, the pulp undergoes bleaching. Bleaching methods. Elemental chlorine bleaching, old method, highly polluting. Elemental chlorine-free ECF bleaching, uses chlorine dioxide. Totally chlorine-free TCF bleaching, uses oxygen, ozone, or hydrogen peroxide. Modern mills favor ECF and TCF methods to reduce environmental impact. 5. Paper formation. After pulping and refining, the pulp is diluted with water, typically 99% water and 1% fiber, and pumped onto the fourdrinier or cylinder machine to form the paper sheet. Key steps. Wire section, sheet formation. The diluted pulp is spread onto a moving wire, mesh-forming fabric. Water drains through the mesh while fibers start bonding. Suction and shaking remove excess water and improve fiber alignment. Pressing section. The wet sheet passes through heavy press rollers to squeeze out more water. The sheet at this stage is about 50% water. Drying section. The paper is passed over a series of heated cylinders, steam-heated dryers. The moisture content is reduced to around 5 to 8%. 6. Surface treatment and finishing. At this stage, the paper is formed but requires additional processing to improve its quality. Surface coating optional. Clay starch or synthetic polymers are applied to enhance smoothness, printability, and gloss. Common coatings include glossy, matte, or satin finishes. Calendaring smoothing and thickness control. The paper is passed through polished steel rollers calendars. Too smooth and compress it. Higher pressure results in glossier and thinner paper. 7. Cutting, reeling and packaging. Reeling and cutting. The finished paper is wound onto large rolls, jumbo rolls. These rolls are cut into standard sizes, for example, a 4-letter size, newspaper rolls. Specialty products, for example, tissue, cardboard, undergo further processing. Quality control. Final tests, check for weight, thickness, brightness, strength, moisture content, and surface finish. Defective sheets are recycled back into the process. Packaging and distribution. Paper is wrapped, labeled, and shipped to printers, publishers, packaging companies, or consumers. 8. Sustainability and environmental considerations. Modern paper mills focus on reducing waste, recycling materials, and minimizing pollution. Water recycling. Closed-loop systems reuse water to reduce consumption. Energy efficiency. Mills use biomass or waste heat to power operations. Chemical recovery. Craft mills recover chemicals from black liquor for reuse. Recycling programs. Many mills process old paper to create new products. In-depth analysis of the paper mill process. Paper manufacturing is an intricate industrial process that combines wood chemistry, mechanical engineering, and environmental science to transform raw materials into various types of paper products. Below is a highly detailed exploration of the entire process, covering advanced aspects such as automation, sustainability, and different types of paper production. 1. Raw material sourcing and preparation. The paper mill uses 3 primary sources of fiber. A virgin wood fiber, derived from trees such as pine, spruce, eucalyptus, and birch. The type of tree affects the paper's properties. Softwood fibers, for example, pine, spruce. Long fibers for strength. Hardwood fibers, for example, eucalyptus, birch. Short fibers for smoothness. B. Recycled paper fiber. Comes from used office paper, newspapers, cardboard and packaging materials. Must undergo sorting, de-inking, and cleaning before reuse. C. Non-wood fibers. Alternative sources. Bamboo, hemp, straw, sugarcane, bagasse, cotton, and even agricultural waste can be processed into pulp, used for specialty papers like currency notes, archival paper, and eco-friendly products. Wood preparation steps. Debarking logs are fed into a rotating drum or high-pressure water jets to remove bark. Chipping. The logs are sliced into uniform wood chips. 1 to 2 centimeters. Chip screening and storage. Chips are sorted, and oversized pieces are reprocessed. 2. Pulping. Separating fibers. The goal of pulping is to break down wood or recycled material into individual cellulose fibers, while removing unwanted components like lignin and resins. A mechanical pulping. High yield, low cost. Wood is ground or refined using mechanical forces. Produces weaker, more opaque paper, for example, newsprint, catalogs. Common methods. Stone ground wood pulping. SGW uses rotating stones. Thermomechanical pulping. TMP uses heat and mechanical refining. Chemithermomechanical pulping. CTMP uses mild chemicals for better fiber quality. B. Chemical pulping. Strong and durable paper. Uses chemicals to dissolve lignin, leaving only cellulose fibers. Produces stronger, higher quality paper, for example, Office paper, packaging. Two main processes. Kraft sulfate, process most common. Produces brown pulp, can be bleached. Sulfite process, produces whiter pulp, but less common due to environmental issues. C. Recycled paper processing. Paper is shredded, mixed with water, and treated with surfactants to remove ink. Fibers are cleaned and refined for reuse. 3. Pulp refining and cleaning. Before paper making, the pulp must be refined and cleaned to ensure quality. Refining, beating. The pulp is passed through refiners that break down fibers to improve bonding. Refined fibers create stronger, smoother paper. Cleaning and screening. Centrifuges remove heavy particles, for example, sand, metal. Fine screens filter out undissolved wood fragments. 4. Bleaching for white paper. Bleaching removes residual lignin and impurities to produce whiter pulp. Modern bleaching methods. Elemental chlorine-free ECF bleaching uses chlorine dioxide. Totally chlorine-free TCF bleaching uses oxygen, ozone, or hydrogen peroxide. Oxygen delignification reduces the need for harsh chemicals. Environmental concerns and solutions. Old chlorine-based bleaching created toxic dioxins. Modern mills use closed-loop water systems to recycle bleaching chemicals. 5. Paper formation, sheet making. The cleaned pulp is now ready for sheet formation using a fourdrinier or cylinder machine. Key steps. Headbox fiber distribution. The pulp, 99% water, 1% fiber, is sprayed evenly onto a moving wire mesh. Fibers begin forming a mat as water drains. Wire section, water removal. Gravity and vacuum suction remove excess water. The fiber mat moves forward, forming a continuous web. Press section compaction. The wet paper is squeezed between heavy rollers. Water content is reduced from 75% to about 50%. Drying section, evaporation. The paper is dried using heated steam cylinders. Water content drops to 5 to 8%. 6. Surface treatment and finishing. Once dry, the paper undergoes additional treatments. A. Sizing, water resistance. Additives like starch or synthetic resins are applied to improve printability. B. Coating, smoothness and gloss. Clay, calcium carbonate, or synthetic polymers are applied. Coatings affect paper brightness, gloss, and ink absorption. C. Calendaring, smoothing. The paper is pressed between polished rollers for a smooth finish. 7. Cutting, reeling, and packaging. Final steps. Reeling. The paper is wound into massive rolls, several meters wide. Cutting and trimming. Rolls are cut into standard sheet sizes of 4. Letter. Legal. Quality control. Inspectors check thickness, strength, opacity, and brightness. Packaging and distribution. Paper is wrapped and shipped. 8. Specialized paper manufacturing. Some mills focus on specialty paper, such as tissue and toilet paper. Uses lightweight, highly absorbent pulp. The drying process includes scraping the paper off cylinders for softness. Cardboard and packaging. Uses multiple layers of unbleached kraft pulp for strength. Corrugation machines add ridges for extra durability. Security and currency paper. Uses cotton or linen fibers for durability. Embedded with watermarks, threads, and holograms. 9. Sustainability and environmental impact. Energy efficiency. Many mills use biomass energy from wood waste. Cogeneration plants recover steam energy. Water recycling. Modern mills recycle up to 90% of processed water. Effluent treatment removes chemicals before discharge. Carbon footprint reduction. Sustainable forestry ensures replanted trees offset CO. Mills work towards net zero carbon emissions. Advanced insights into the paper mill process. Paper mills have evolved into highly efficient automated facilities that integrate precision engineering, chemistry, and environmental sustainability to produce various types of paper. Below is an even deeper dive into the technical, operational, and economic aspects of the paper-making process. 1. Advanced wood processing and fiber sourcing. The quality and type of paper produced depend heavily on the fiber characteristics. A. Wood selection and optimization. Different wood types impact paper properties. Softwood, pine, spruce, fir, gives long fibers, high tensile strength used in packaging, tissue. Hardwood, eucalyptus, birch, poplar, gives short fibers, smooth surface used in fine printing paper. Mixed fibers gives balanced strength and smoothness. Mills use computerized sorting and blending to optimize fiber quality. B. Alternative fiber sources. Beyond traditional wood, mills experiment with Agricultural residues, straw, bagasse, gives used in eco-friendly paper. Textile waste cotton, linen, gives high-quality, archival and security paper. Algae-based paper gives an emerging sustainable alternative. 2. Next-generation pulping technologies. Pulping has seen significant innovation to improve fiber yield, energy efficiency, and environmental impact. A. Advanced chemical pulping. Modified kraft process. Uses oxygen delignification to remove lignin more efficiently, reducing chemical use. Closed-loop recovery. Chemicals are captured, purified, and reused common in modern mills. Black liquor recovery. The byproduct of kraft pulping, black liquor, is burned in recovery boilers to generate energy. B. Enzymatic and biopulping. Uses fungi or enzymes to break down lignin instead of harsh chemicals. Reduces energy consumption by 30 to 40%. C. High consistency, mechanical pulping. Uses precise steam and pressure control to maximize fiber separation with less energy loss. 3. Automated paper sheet formation. Paper sheet formation has evolved to use real-time sensors and AI-driven monitoring. A. Modern four-linear and twin-wire machines. The pulp suspension is computer-controlled to ensure even fiber distribution. Laser-guided thickness sensors ensure uniformity. Multiply formation mills can create layered paper sheets for specialized uses, for example, multi-layer cardboard, coated papers. B. Advanced water removal. Water is removed in 4 stages. Gravity drainage, 20% solids achieved. Vacuum suction removes another 10% of water. Pressing section further reduces moisture to 50%. Infrared and steam drying brings moisture to 5 to 8%. For high-tech surface treatment and coating. Coatings enhance durability, printability, and special functions. Of functional coatings. Waterproof coatings gives used in food packaging, outdoor signage. Antimicrobial coatings gives integrated into medical paper products. Barrier coatings gives replace plastic in eco-friendly packaging. B. Digital and inkjet optimized coatings. Special formulations prevent ink bleed and enhance color vibrancy. Nano coatings are being developed for smart paper applications. C. Calendaring and finishing. High-pressure rollers control paper smoothness, gloss and thickness. Digital calendaring allows variable texture control on the same sheet. 5. Cutting, reeling, and quality control. Once the paper sheet is complete, the final steps ensure precision and quality consistency. A smart reeling and slitting. High-speed reels automatically adjust tension to prevent defects. Computerized blade adjustments ensure minimal waste. B. Quality control with AI and machine learning. X-ray thickness scanners measure uniformity. Optical brightness sensors check for color and brightness variations. Defect detection, AI pinpoints inconsistencies. 6. Specialized paper manufacturing. Mills produce custom paper products using advanced techniques. A. Security paper banknotes, certificates. Uses watermarks, security threads, and embedded holograms. Fibers include cotton and polymer blends for durability. B. Ultra-lightweight papers. Used in Bible printing, airline manuals. Requires precise fiber blending and ultra-thin coatings. C. Synthetic and smart papers. RFID embedded paper. Used in logistics and passports. Printable circuit paper. In development for interactive packaging. 7. Environmental sustainability in modern mills. A. Water and energy efficiency. Closed-loop water systems gives recycle up to 90% of processed water. Energy recovery from black liquor gives supplies 60 to 80% of mill power. B. Carbon-neutral paper making. Biomass cogeneration replaces fossil fuels. Carbon capture projects are being developed. C. Waste reduction and recycling. Zero waste mills. Gives aim to reuse all byproducts. Circular economy paper gives new papers are designed to be recycled more efficiently. 8. The future of paper mills. AI-driven smart mills. AI predicts equipment maintenance, reducing downtime. Blockchain paper tracking ensures supply chain transparency. B. Biodegradable and plastic-free packaging. Developing plant-based waterproof paper to replace single-use plastics. Compostable paper coatings being introduced. C. 3D paper engineering. Mills are experimenting with paper-based 3D materials for construction and packaging. Conclusion. The evolution of paper mills. Paper manufacturing has transformed dramatically from a traditional industry into a high-tech, AI-powered sustainable sector. Modern mills are carbon-efficient, waste-conscious, and fiber-diverse, paving the way for plastic alternatives and smart paper products.